All right, so in this section, the book calls it the natural log integration. I really don't like that title because it makes it sound like we're going to take the antiderivative of natural log, which is not the case. So I'm going to title this Integration to Get a Natural Log. And to start off with, I want to take a look here on the left side of our screen. If I were to ask you right now, what is the antiderivative of 1 over x, many of us would probably think about using our power rule and say, oh, that's just the integral of x to the negative 1 power. I know how to do that. I add 1 to the exponent, which makes it then to the 0 power, and I divide by the new exponent, which is 0. That's a problem. We can't divide by 0. And so our power rule, as nice as it is, working for positive numbers, negative numbers, and even fractional numbers, it does not work for negative 1. So what do we do with this rule? Well, take a look at what I have below. If I were to ask you what is the derivative of natural log of absolute value of x, that is just 1 over x. We saw that the other day. And so an antiderivative, if I go back up here and I ask myself the derivative of what gives me 1 over x, well, I now could see from below that it was the derivative of the natural log, which gave me that antiderivative. And so this is the rule that we are going to be focusing on today, is that if I can get my integral to look like 1 over x or 1 over u if I'm using u substitution, it's going to turn into a natural log. Just a quick side thing, we always have absolute values. We always include the absolute values with our rule. Kind of the quick and dirty way of why that works is we know that the natural log of x and the natural log of absolute value of x both give us 1 over x as a derivative. So as part of our rule, we're going to include or use the function that has the biggest domain, that applies to the most values of x. So this one right here would apply for any value of x any value of x not equal to 0, whereas if I didn't have the absolute value bars, it would only be values of x greater than 0. So our rule is this, so that it includes every single value of x except 0. All right, so let's look at a few. And so if we're going to use u substitution, and to tie it in with my rule below, after my substitution, if it's going to turn into a natural log, I want it to look like this. Okay, that's what we're really hoping to see. So do I have that here? And the answer is yes. One of the keys and one of the patterns you're going to look for is that if you see this in your integral, so if you see that you have some function on the bottom, oops, that was meant to be blue. There we go. If that was some function, and at the same time I see that function's derivative in my numerator, again, remember it can differ by just a constant, I'm going to be thinking about using u substitution to hopefully turn it into a natural log. So in this case here, that's what I see. I see that in my denominator, if this is my u, well, what's the derivative of x cubed plus 1? It's a 3x squared. And so although I don't have the 3 in front, I at least get a 3x squared. I get the x squared. And so that's how I'm going to proceed here. And from this point forward, it's going to be pretty much the exact same as with our u substitution as before. U is going to be x cubed plus 1. As a result, the derivative is 3x squared dx. And let's go ahead and substitute. My whole denominator gets replaced with u. What do I have left? I have an x squared dx. And so I need to divide that 3 to the other side. And so there's the 1/3 being divided du. Okay, so the substitution is the exact same. The difference now is the antiderivative of 1 over u. Before today, we didn't know how to do that. The power rule wouldn't work. Now I do know what that rule is. That's going to turn into a natural log. So that's going to be a natural log absolute value of u plus c. That is our antiderivative. Unfortunately, it's in terms of u and not x. And so to finish this problem off, I will just convert and turn the u back into the x cubed plus 1 plus c. And that would be our final answer. All right, similar example, except we have a few trig functions in there. But we have the same sort of a pattern here. We have a fraction, and what I want you to recognize is that if that was my u, what's the derivative of cotangent? Well, the derivative of cotangent, although it's negative, is negative cosecant squared of x. And so we have the same pattern. I have some function in the denominator, and its derivative is on top. Again, small asterisk, its derivative differing by only a constant is in the top. And I can now use u substitution again to make it match our new rule for today. So cotangent gets replaced with u. What do I have left? Cosecant squared dx, which is right here. I got to get the negative to the other side. So there's the negative moved to the other side. And what do you know? We have our same rule. So we have negative natural log, absolute value of u plus c. There's my antiderivative in terms of u. Turn it back. So we get negative natural log, absolute value of cotangent of x plus c. And that would be my final antiderivative. All right, so this one's a little different. Note my kind of trial and error. If we were going to try to match the pattern that we saw before, and we were going to try to let u be x plus 1, remember we would want to see the derivative of that function in my numerator. Well, unfortunately, the derivative is just 1, and I definitely don't have 1 in my numerator. I have an x squared minus 3x plus 2. So that whole idea is out. On the flip side, some of you may think that we should try letting u be the x squared minus 3x plus 2. And that's a good attempt. It's wrong, unfortunately, but many of you may think that because the derivative does kind of give me an x, which you may see down here in the denominator. I get a 2x minus 3, but there's actually two problems with it. One, the big difference is we don't actually have an x. We have a 1 over x plus 1. And what I have right here is not a 1 over x, it's a just 2x, or just an x. So obviously x and 1 over x are two different things, and if you were to try to physically make this substitution, you'd run into weird things like your integral would have like a 1 over du in it. And that should be your red flag that something's wrong. You should never be dividing by du in the integral. So what do? Well, this is what we call an improper rational function. It's improper because the degree, which is the highest power of x, which in this case is 2, the degree of the numerator, 2, is bigger than or equal to the bottom, which the bottom has an implied degree of 1 because it's x to the first power in the denominator. So let me clear out my red things here. So it's improper. The degree of the top is equal to, or in this case, bigger than the bottom. We are going to break this fraction apart using long division, polynomial long division. So let's refresh ourselves on how that works. I'm going to divide the x squared minus 3x plus 2 by x plus 1. And the hope is that when I divide it, it's going to break up into a bunch of smaller pieces being added or subtracted together that I could maybe integrate individually. So in this process, I asked myself, what do I need to multiply the x by to cancel out the x squared? Well, it needs just one more x. So I put the x over the same kind of what I call the x column right here. And then we multiply the x through. So this becomes x squared, and then x times 1 is plus x. And we subtract straight down. So x squared minus x squared cancels. Negative 3x minus x gives me a minus 4x, because remember, we're subtracting down. Okay? And we carry the plus 2 down. And we play this game again. What do I need to multiply x by to cancel out now the negative 4x, which is in front? I need a negative 4. And so there's my negative 4. I multiply it through minus 4x minus 4, and I subtract straight down. Negative 4x minus 4x, or excuse me, negative 4x minus negative 4x cancel. 2 minus negative 4 gives me a remainder of 6. And so what that means is that this integral can break up to x minus 4, which is what I have on the top of my division. And then plus, it's going to have a remainder of 6 divided by what I was trying to divide into it, which is x plus 1. Okay, that's a dx there. That's how this fraction would break apart with long division. And why it's useful here is that now I can integrate the x individually, the negative 4 individually, and now this last fraction, you might see the pattern now, is going to turn into our natural log. So let's go ahead and do it. The x turns into an x squared over 2 when I integrate it. The negative 4 turns into a minus 4x when I integrate it. And for the 6 over x plus 1, I'll leave the substitution to you. But if you were to let u be x plus 1 and run through your u substitution, that would turn into 6 natural log absolute value of x plus 1. And then, of course, plus c. And that is our antiderivative that we were able to figure out from breaking up the fraction with long division. Some of you may remember synthetic division, which would apply in this case. Synthetic division, though, only works if you're dividing by a linear function in the denominator. So in this case, since x plus 1 is linear, you could do synthetic division. But if I had made this an x squared plus 1 in the bottom, you would have to do it with long division. Long division always works, so that's why I like to teach it with these types of problems. All right, so this one is very similar to the ones that we've done in the past. It looks like we have the right pattern, and I just want to show you that if I let u be my denominator, what would the derivative of that be? Well, the derivative is going to be 2, comes out front, keep the inside function the same, drop the power by 1, making it 1, times the derivative of the inside. The derivative of x plus 1 is just 1, so dx. This is close. The derivative is a 2 times x plus 1. What I actually have, though, is a 2 times x. And it may feel like they're similar, or that we can do it that way. The problem is, remember, I said that the derivatives can differ by a constant multiple, not a constant addition. Okay, so x and x plus 1, no good, because they differ by a plus 1. An x and a 2x and a 3x and a 4x, those are okay because they differ by multiplying by different numbers, not adding. So this is not going to be a good choice for us. So we think back to our u substitution, and it's okay. This may or may not be a log. Let's see. I'm going to try our one of the things we talked about last time is let's let u be the inside of my composition. So if u is x plus 1, okay, we get our derivative to be 1 dx, and it might look like that's not a good choice because it doesn't give me an x to cancel out on top, but let's see what happens to our substitution. The nice thing, the one thing I do like about this right now is that it gives me a u squared on the bottom. It gives me the base now is a u, plain old u. It's going to combine nicely with other u's to any power that we may have. And on the top, we have 2x dx. Okay, so I'll just make that one substitution right now. We're not done. So, okay, we need to get rid of the x and the dx. Well, right away, I see that dx and du are the exact same thing. So I can just freely replace the dx with just a du because they're equal. I still have my 2. What can I replace x with? Well, I look at my rules of substitution up here, and if I manipulate this and get x all by itself, I see that x is just going to be u minus 1. So I can replace x with u minus 1. Okay. There's the substitution. How is that helpful? Well, if I distribute, look at what this turns into. I get a 2u minus 2 du over u squared. And one way that we can simplify a fraction is that if we have a single term in the bottom, or sometimes referred to as a monomial in the bottom, we can divide it into each of the individual terms individually. So I get the integral of 2u over u squared minus 2 over u squared du. Okay? And so what's nice now is that this u can cancel out with that u, and I have two functions now being subtracted, and I will take their antiderivatives individually. The first one is our natural log rule. This will be just 2 natural log absolute value of u. And then the second one is just going to be power rule. Remember, this is 2u to the negative 2. So it's going to be minus 2u to the add 1 to the exponent, and we divide by the new exponent, plus c. So those double negatives will go and cancel out. And so my final answer I'll do in black here. Oops, that's probably not enough space. My final answer I'll put here on the left side will be 2 natural log absolute value of u, which was x plus 1, and then plus, let's see, 2u to the negative 1. So 2u to the negative 1 means divide by u, and u is x plus 1 plus c. Okay? So there in black, bottom left, would be my antiderivative. All right, I just wanted to throw this one in here just to keep you honest. Sometimes our book does I like it, you may not, but our book will throw old u substitution problems into the new sections, meaning that not all of your answers may be natural logs, and you need to be honest with yourself and really look for the correct pattern when you do it, because when I give you an antiderivative, I'm not going to tell you, hey, this is going to turn into a natural log. So what do I see in this problem? Well, I do see a composition right here. Natural log is being cubed. And what I also like about that choice, if that's my u, what's the derivative of natural log? Well, the derivative was 1 over x. Okay, think of that as I'm dividing by x, 1 over x. And that's what I have right here, a 1 over x. You could rewrite this problem as 2 times 1 over x times 1 over the natural log of x cubed dx. And we could see that the 1 over x here will cancel out the 1 over x there when I do my u substitution. And that's what we need to do in this example. So the 2 I'll pull out front, and let's go ahead and substitute. I get 1 over u cubed. And what's left? 1 over x dx, which is exactly what I have right here. They can be replaced with just du. And so with that substitution, I get a 1 over u cubed, which is not a natural log. A natural log will only be 1 over u. Anything else, you're using the power rule. So let's do it. This is going to be 2, let's see, u to the negative 3 power. We add 1, making it negative 2, and we divide by negative 2 plus c. There's my antiderivative. Let's go ahead and turn it back into x's. 2's cancel. I still have the negative there, so it'll be negative 1 over u squared, which is natural log of x now squared, plus c. All right, so with our integrals now, at this stage we can actually, and you need to know all the integrals for all 6 trig functions. We've seen 2 of them already. The first one here, we know the antiderivative of sine will be negative cosine of x plus c, and the antiderivative of cosine is positive sine of x plus c. We've dealt with those. But now within this section, we can actually prove what the antiderivatives would be for the other 4. I would recommend just having these memorized. You don't want to take the time of proving these rules every single time. I'll just tell you how you would go about it. With tangent, you could think of tangent as sine over cosine. And at this point here, you could use u substitution. You could let u be cosine of x, and I'll leave the rest of the work for you. But if you were to run through that, it would turn into a natural log with a cosine in the middle. And since the derivative of cosine gives me a negative sign, when you're all done with it, you're going to get a final answer of negative natural log absolute value of cosine of x plus c. Okay, so again, that rule there, I would recommend just memorize it. That is the antiderivative now of tangent, but if you were in a bind, you could derive it pretty easily by rewriting tangent and doing u substitution. The other three, cotangent has a very similar process of proving it, but it will have a rule of natural log sine of x plus c. The last two, for sure, the proofs are a lot harder. You just need to have these memorized, and I'll tell you a little trick I have of memorizing it. So here are the rules. It'll be the natural log of secant of x plus tangent of x, both inside of an absolute value being added together. And for cosecant, it's going to be negative natural log absolute value cosecant of x plus cotangent of x plus c. And again, those are rules that we just need to have memorized. But here's how I remember secant and cosecant. I have to remember that they are both going to be natural logs with absolute values. What goes inside, or what gets added together inside the absolute value, is essentially the two pieces of its derivative. And that's really just a kind of a coincidence. But the derivative of secant is secant tangent. And that's what you see inside, a secant and a tangent being added together. For cosecant, what's the derivative of cosecant? It's a negative cosecant and cotangent. And what I like is that's what you see on the inside, cosecant and cotangent being added together, and it tells me that there'll be a negative in front because its derivative is also negative. So let's do one last example just to tie together our new rules. I would recognize that this is asking me for the antiderivative of tangent. Unfortunately, it is not the parent function, so I need to use my u substitution. U will be the inside of that composition, which is 2x. The derivative of u then would be 2 dx. We make our substitution. The 3 I'm going to pull out front. I get tangent of now u, and the dx, I have to divide the 2 over, will get replaced with 1/2 du. And now this is a rule I've asked you that you need to have memorized. So it's going to be 3 over 2 times the antiderivative for tangent, which is negative natural log absolute value of cosine of u plus c. Okay. There's my rule, and now we just convert it back to x's. Negative 3 over 2 natural log cosine of 2x plus c.